Balancing redox reactions. Now, balancing reactions, you know how to do that. We're going to have to tweak a little bit, and it's going to look a little bit weird at first, but it actually follows a nice, neat little process. However, we're going to be working with integers, and nobody likes working with integers. So that's sort of the two things to kind of keep in mind as we get into this. Now, we're familiar with balancing reactions by inspection. We just look at it and balance them. So what I would like you to do is pause this if you need to, balance that reaction really quickly, and then we'll come back to it in a moment. Excellent. All right, so I know some of you didn't pause it, but that's okay. This is what you'd end up with. Now, if we look at this thing as a redox reaction, then we want to first identify what's been oxidized and what's been reduced. And you should be pausing it here for that as well, but if you haven't, sulfur has been oxidized. It goes from a -2. We talked about last time how to come up with oxidation numbers. And oxygen gets reduced. It goes from a 0 to a -2. And if you're not familiar with this yet, anytime you see something that's an element on one side and a compound on the other side, great place to start is to see what it's done, and the other stuff has done something different. Hydrogen compound on both sides. So hydrogen in almost all compounds is +1. So we can right away say hydrogen was not involved. So we can actually start to eliminate things pretty quickly. Okay, now let's look at the total number of electrons gained and total number of electrons lost, because we've got things losing electrons and other things gaining electrons, and the numbers have to match up. So sulfur, if it's gone from a -2 to a +4, that's 6 electrons. And there's 2 atoms doing that, and that comes from the balancing numbers. So a total of 12 electrons traded places. Okay, that means oxygen has to have done a total of 12 electrons, and indeed it does. We've gone from 0 to -2, 2 electrons, but 6 atoms doing that. So total of 12 electrons in both cases, and that's great. What I want you to do, if you haven't done it, is this reaction, balance this one, again, by inspection, pause it, and the fact that it takes place in acidic solution we'll talk about in a couple of minutes, but take a moment, pause, and balance. Okay, again, some of you might not have, but we're going to keep moving on. So when I did it by inspection, this is what I came up with. Now I want to do the same thing I did last time. I want to identify oxidized and reduced. Well, iodine starts out as neutral and ends up in a compound. Ends up in a compound with oxygen. Oxygen is always negative, so iodine must be plus. So that means, I did that backwards, that iodine gets oxidized and then chlorine must be reduced. Okay, and if you didn't come up with the oxidation numbers, make sure you know how to do that, and please take some time and do that and make sure you end up with a +5 to a -1 and 0 to a +5. Okay, do the same thing. Total electrons lost, total electrons gained. And if I look at chlorine, 2 atoms are gaining 6 electrons, going from +5 to -1. That's 12 electrons. And then iodine going from 0 to +5 is 5 electrons each, and 2 atoms are doing that. So that's only 10 electrons. Now that's a problem because total number of electrons lost and total electrons gained aren't the same. Now you could say, well, couldn't I do some multiplying and make it work out? And the answer is yes, but what do we do with the fact that, how do we balance it without going through all of this? Okay. Now, 2 things to think about in terms of where we went wrong. We didn't really go wrong, but what did we miss? We know that part. And we also know that if electrons are lost, they have to go somewhere. If they're going to be gained, they have to come from somewhere. There's no magic happening. But we also left out or ignored or didn't do anything with this acidic solution. What does acidic solution mean? Well, it means we've got water in there. And water could behave as a reactant. We know that from our acid-base unit, that if nothing else, it can take or donate protons. We also have H+, or hydronium, I guess, but we've got a bunch of those kicking around, and those have charges. So what we're going to do is we're going to go through the same reaction. We're going to balance in an acidic solution. We're going to go through the steps in detail, and then at the end I'm going to give you a summary. It's going to look long, particularly if we build it up and well, you'll see what I'm doing. If your thing looks like my thing, where every time we kind of write it out again, it's going to get long. And there's no need to make it that long. So I'll try and describe what I mean in terms of short forming it. So there's my reaction. The first thing I'm going to do is I'm going to write the half reactions. All right, so I'm going to write the part that gets oxidized and the part that gets reduced. Here's the best part. It doesn't matter which one is which. All I have to do is use the chlorine, what happens to it, and then same thing with the iodine. I don't need to know which one is oxidation, which one is reduction. You'll notice it for me on mine, I've left big gaps here. And part of that is, as I would be filling this in, I would actually be filling in the gaps rather than rewriting the reaction the next time down. Second step is I balance everything except hydrogen and water. So it's in hydrogen and oxygen. It's in acidic solution, so I've got water and I've got hydrogen, I've got H pluses, and I've got water. So I've got other sources for hydrogen and oxygen, so don't worry about those just yet. Well, the only thing I really have to do with that one is the iodine. Okay, going from iodine to the iodate, I need to have a 2 in there. And that takes care of balancing the iodine. Chlorine was already balanced, so 1 on either side. Next step is I balance oxygen by adding water. Now I want to pause here for a moment. What we're doing, you don't have to pause, what we're doing here is something that works really well on paper. We're not saying that this is how the reaction actually happens. This for us is again, it's kind of a bookkeeping kind of thing. As we go through all the element accounting and the electron accounting, this works, and then we're going to bring it all back together at the end. So it's not necessarily the case that the reaction actually balances oxygen using water. We're going to, but the reaction isn't forced to. Okay, well, in the first reaction, there are 3 oxygens on the left, none on the right, so I need 3 on the right. And I add 3 waters to the right. In the second reaction, there were now a total of 6 oxygens on the right. I need 6 on the left, 6 waters. Now again, this is what I was talking about before about filling in these gaps. So I'm writing it out each time anew, but you don't necessarily have to if you can squeeze it in the gap. Okay, next step, balance hydrogen. All right, now when I was fixing up oxygen here, I brought in all kinds of hydrogen that weren't there in the first place. Well, I'm going to balance hydrogen now by adding H+. So in the first reaction, which had a total of 6 hydrogens on the right, I need 6 on the left, I add 6 H+. Same thing with the other one, I had 12 hydrogens on the left, I'm going to need 12 on the right. Now, again, pausing here for a little babble, it's not necessarily the case that you'll add water to the left side of one, right side of the other. Maybe, but not necessarily. Okay, so don't look at that pattern. It won't necessarily be that you'll add hydrogen to one side and not the other, or one and the other side of the other. Or you might not add any hydrogen at all. It all depends on how it works out. Next step, balancing the charge. Now, if things go wrong, this is where it happens. So please pay extra careful attention to this. And the reason it goes wrong is because of these negative charges. So we have to look at negative charges in our balancing stuff. Okay, in the first one, I've got -1 plus 6. I have a total of plus 5 on the left-hand side. And over here, I've got -1, and this is neutral. So that's my charge. I cannot change, I'm adding negatives. So the only thing I can do is take the one that's more positive and bring it down to the one that's more negative. Okay, in other words, what I'm doing is I'm going to be adding 6 electrons. Next one, no charge. No charge, -2 plus 10, plus 12, I'm one step ahead of myself, plus 12, total is plus 10. I need to bring that down. I take the one that's more positive, bring it down to the one that's more negative. Well, this one's a 0. So what I'm going to be doing is going to be adding 10 electrons to balance the 10 positive charges. So 10 electrons. Now, we already knew, kind of running into this before, that we had an unbalance of electrons. Our next step is to fix that. So our next step is that the total number of electrons lost equals total number of electrons gained. Let me go back, we'll do it here. Okay, so before we jump into that too much, one of these will be on the left, one of these will be on the right. If you end up putting electrons on the same side, there's a mistake somewhere. Um, Having said that, if the first one said, okay, this one's on the left, this one's automatically on the right, if I didn't make a mistake the first time, right? So make sure you work it through in detail each time. All right, so going back to total number of electrons, lost and gained. This one is 6 electrons on one, 10 electrons on the other. They need to be the same. Hey, this is like that thing you did in solving equations in math where you multiply the first one by something, multiply the second one by something. If I multiply the first reaction equation by 5 and the second one by 3, I'll end up with 30 electrons each. Okay, so 30 electrons, 30 electrons. That's what we're after. Doesn't have to be 30, has to be the same. Next step is to reduce and combine. So I'm bringing all of this stuff together and taking out some of the stuff where there's overlap. If it's on the reactant side and on the product side, I can at least partially cancel it out. So how's that work? Well, my 30 electrons and 30 electrons cancel out. Number of electrons gained on the top one equals number of electrons lost on the bottom one. That's the whole point. But I also have hydrogens on both sides, H pluses. Well, I've got one that's 30, one that's 36. So I can cancel out all of one with most of the other, leaving me with a 6 hydrogen left over. And similar thing with water. I can cancel out all of one with most of the other, leaving me with 3 waters. Then I combine those. Now my 3s and 6s are 3 and 6 are kind of in the wrong spot for this, so we'll drop down an extra line. Combining them together, I've got 5 chlorates, 3 iodines, 3 waters, 5 chlorides, 6 iodates, and 6 H pluses. That is a balanced redox reaction using half reaction method. All right, so what's coming up next is a summary list of how you do this. And there it is. You've already got the steps. I'll give you a chance to pause it if you want. But those are the steps. And it looks like a lot. And once you get used to it, until you get used to it, I should say, it is a lot. But once you get used to it, it actually goes along pretty quickly. And then what I'm going to do is I'm going to give you one to try. So here's the reaction to try, and what I've got below it is an answer. So what I want you to do is, in preparation for class, is to try that so that, you know, if you get stuck, here's what I got, and then there's the final answer. So please try it so you have something to compare it with, and then we'll do ones where you have nothing to compare it to once we get to class. And I'll see you there.